Hi everyone, my name is Alex Christie. I'm a research fellow at Imperial College London. I work on a project trying to speed up evidence synthesis with AI in conservation. I work with Sam, Neil, and Sardik. But there's just a support act today. I'm just going to explain a little bit more about the context of this project that Radhika, Shrey, and Kacper have worked on over the summer during an internship, and they're going to explain a bit more about their projects and what they did. But I need to give you a bit of context so that you kind of understand what they're going to be talking about. So I'm just going to start with talking a bit about the biodiversity crisis and what we're trying to do to solve it. So many of you know about this. We've a million species that are facing extinction, and without concerted conservation action and good knowledge on which actions work and which don't, we're going to see further accelerated loss of species if we don't do this. But what you might not know is that there's also an evidence crisis in conservation. So we found, the research in our group in zoology has found that a lot of conservation managers, practitioners don't use scientific evidence to inform what they do. They tend to rely on personal experience, anecdotes, and the advice of colleagues. So there's a big project that we're working on, conservation evidence, trying to improve the translation of scientific evidence to support decision making and practice. So one example of the lack of evidence use is the Common Agricultural Policy, which was the EU subsidy scheme that incentivised farmers to do more environmentally friendly farming, essentially. And a review of that found that only 54% of the actions that were measures that were proposed in that were actually known to show any clear benefits. So a lot of this money was being wasted on actions that were ineffective, and we really can't afford to be doing that in conservation because we often have very limited resources and time. So conservation evidence project is something that Sam and I work on. It's led by Phil Sutherland, and its aim is to essentially synthesize all the evidence in the world on the effects of different conservation actions on biodiversity. So it's quite a big synthesis project, and what we do is we basically manually, we haven't, but a team of postdocs have manually screened over 1.5 million papers, and so those are papers testing conservation actions and looking at the sort of the effects of those on biodiversity outcomes. And so they screen those and narrow those down into nearly 9,000 directly relevant studies now. And that summarization process then takes place, and we put those summaries freely accessible online, and we also assess the different actions and how effective they are, and make that freely available to everyone in conservation. But as you can imagine, this process is really slow. It's all manual. And we think about 75 years of research time has gone into it so far. So it's been over the past couple of decades that this has been taking place. And what we're finding at the moment is really hard to update the evidence that we've got there now, because there's just so many studies out there. So we can only really add a few hundred studies per year. So we're falling behind. So we've got to move faster. And we think AI obviously could really help us do that. So as a bit of context, the projects that the students are going to talk about are kind of part of a wider plan that we're trying to develop this end-to-end system pipeline to do evidence synthesis on a big scale, much more efficiently for this conservation evidence project, but also more widely. And so there are kind of three. I've just broken this down to kind of three main parts. First, we're trying to use AI to automatically retrieve and categorize the relevant papers from academic journals, but also from the grey literature. So basically everything outside of academic journals is the easiest way to explain what it is. So we're trying to do that process of finding the papers and categorizing them. Second stage is to then extract the information we need to summarize that evidence, but also to work out how good of quality is that evidence. So should we trust it or not? And then finally, we're trying to build an interface so that practitioners, decision makers can interact with the evidence much more intuitively, because we've got a website. But that website is often quite hard to navigate, and people really want quick answers. So we're looking at developing a sort of chatbot interface that can provide decision makers with really easy access to the evidence they need. So the 3 students that are going to talk today, they did Europe internships with us over the summer. And they've been working on 2 different parts of the pipeline I just mentioned. So Kacper and Shrey, they've been looking at the first part, and specifically looking at the grey literature. So Sadek has been focused on the academic literature from journals, but Kacper and Shrey have been looking at building a scraper and classifier to get at the grey literature. And Radhika has been looking at the other end of the pipeline, so looking at how we can evaluate large language models in how good they are basically at answering decision makers' questions based on the evidence database that we already have. So that's me teeing them up. I'm going to now hand over to them. I guess probably makes more sense to press the Shrey to go first, and then Radhika. That's up to you guys if you've got an order.
We have an order of writing first.
Sorry. Yeah. It's all right. I do not fast you want me to see. You can see on the side.
So, as I mentioned, the main aim of the editor was evaluating the ability to answer questions that conservationists may have. And so the way we did that was using retrieval augmented generation and RAG pipelines essentially, and they basically occur in 2 stages. And so the first is retrieving the correct document needed from our database, which we're going to be using the Sleep databases for this basis. And then the second part is sending this query off to an LLM. And so I know Alec would introduce the conservation evidence database, but just to explain the sort of structure of the documents that we were using, we have synopses, 26 of them in total, and they range over sort of to essentially summarize actions that have been taken for particular sort of types of species. And each of these actions then have it's a document with a series of sections, so you're given more detail about the sort of studies that are relevant. But what happens is that some some actions have no evidence related to them, and so you get sort of a paragraph that says we've seen no evidence yet. And so I think one thing to note is that I ignored the documents without it, so that brings down our database from around 4,000 actions to around 2,800. And so what we were focusing on was sort of key messages like this. So you have sort of comments on certain studies, and the idea is that this was sort of the granularity of what we wanted to look at, because even though there's things like the supporting evidence section and the background information section, we didn't think it was relevant either because perhaps conservationists would be asking specific questions about studies, so that wasn't really the scale that we wanted to look at. And also, we didn't really want to confuse sort of the retrieval setup by having paragraphs across multiple actions. So, for example, background information can contain quite general information, and so that doesn't really help with how we're testing out the system. So if we then look at the way we actually came up with these pipelines, we were following a method that came out in the AWS paper earlier in the year, which aimed to automate this evaluation process. And so the first stage is actually generating the questions that we want to ask. And so these were all generated using Claude 3.5 Sonnet, and they're all multiple choice questions. And so, for example, this is an example of a question that was generated, so it just asks about plant diversity. But we also asked for the LLM to provide some sort of documentation or proof of correctness for the question being generated. And this is actually one to ensure that we were generating questions based off of documents within the C database. And also, this was actually quite helpful, I think, later on when we were doing some comparisons between LLMs and humans. And so having that proof of correctness also helped with filtering that down. But I will come back to that later. And so the generating of questions was automated, as was the filtering. And so what we want to avoid is, as much as we can prompt engineer Claude to generate the right types of questions, we don't want questions where, for example, one answer is X.
Sorry, can I ask a clarification? I mean, why are you generating questions? I missed I don't know enough about the space, but maybe others do. But what's the point of generating a question?
So I think the main aim was so we have a big bank of questions that we can then test the retrieval and the LLMs with, and so we wanted to make it all automated because one, we have a larger bank of questions, and two, so that perhaps we don't want to generate questions where we are expecting, for example, like free form text.
Maybe I'm not being clear here. Are these questions generated by humans or
No, the questions were generated by
and the answers also generated by the LLM?
Yes.
So it's marking its own work.
Essentially, yeah.
But what's the point of doing that?
The main thing that we were testing was ensuring that checking whether the right actions can be retrieved from the database. So by having the question generated based off of one singular action. So the LLM would generate one question per action in the database. And so then when we then go and actually test these RAG pipelines, it's only answering questions about the C database. So this is before we've sort of done broader context of any sort of question that could be asked.
I'm lost, but that's okay. Keep going.
I don't know.
So retrieval augmented pipeline, you sticking an LLM on top of a corporate documents, right? And you ask it questions and it produces a response. But how do you evaluate quantitatively how good that pipeline is? Because evaluating a free-form response is quite difficult. Right. So what Radhika has done is taken a corpus, generated questions, and a multiple choice exam scheme for each one. And then that gives you a way of experimenting with different parameters of your pipeline and having a quantitative score attached to it. So while she did it with one LLM, we weren't testing that same LLM in isolation. We tested lots of different LLMs and lots of different ways that you could build a pipeline. Because at the moment you have no way of quantitatively saying this design decision is better than this design decision.
Yeah, but where I get lost is how do you know the answer is right if you are checking the answers? The LLM creates the wrong question to do it has a wrong answer. How do you know?
You kind of don't, in that you don't, but you've done this across 10 different LLMs, right? So your answer is probably going to be right overall, and the human evaluation that we did showed that it is right majority of the time. So you've got a noisy set to evaluate, basically. But that's about as good as you're going to get, right? Because your alternative is handwriting questions to test this pipeline with, which is never going to scale to any kind of decent size.
And there are two different data sets, which I imagine most will get onto. There's a human check data set where we definitely know the answer right, and there's a bigger data set where it's much bigger sample size that we don't know. 100% it will be answered right. But
so I would suggest let's let Radhika and Kacper and Shrey speak, and then the same questions to the end.
Yeah, I mean the idea of having sort of a documentation section was to make sure that the questions were being generated from the text itself. So hopefully that was a bit of correctness. But if I just then move on to the actual testing of the pipelines, and so this question got two stages that was sort of changing the variables across. So the first is the retrieval mechanism section. So that's what I'm calling the exam conditions section, which is can we pick out the right context to add to the query for the LLM? And then the second is changing the number of LLMs possible as well. And so our first exam condition was just closed book. So this is when just the query and the 4 answers are sent off to the LLM. And so that's just to test sort of inherent baseline knowledge for LLMs for sort of certain topics in conservation. We then had 2 oracle exam conditions. So in the first, we give it the question, but also the document that the question was generated from. And so this is just to check that LLMs are passing the information that it's giving correctly. The third was a confused oracle, so it's still given the correct document, but it's also given one confusing one from the same synopsis. So that's sort of two reasons. One, just because adding context and increasing the context length generally makes elements slightly poorer. But two, for the next section, which is the actual retrieval models, having a length of 2 is helpful. In this case, because this is essentially our best case scenario, right? We have a perfect retrieval, and so we take the best, the correct document, but we also give one on. And so the 3 retrieval mechanisms are sort of standard different ways of querying a database. And so in the first, we take the actions and have them in sort of dense embeddings. In the second, we use sparse embeddings, and then in the third, sort of hybrid setup. So you would take the top 5 from the dense embedding section, the top 5 from the sparse, and then use a re-ranker to choose the best 2. And so if that all makes sense, so that's the first variable. And then the second things that we were varying on are the LLMs. So we checked 10 different LLMs, a mix of open source and proprietary ones, and then sort of different sizes, parameters and structure and things like that. And so if that will make sense, I will move on to the results. So yeah, as Alec mentioned, the unfiltered set is the set of 1,800 queries. And I know there's a lot of numbers, but I think what I wanted to highlight was that we already have like a relatively high baseline closed book accuracy, so everything was above 60%. So that suggests that either the questions are slightly simple, or that the models have some pre-training on conservation. And I haven't highlighted it here, but also the confused results are worse than the oracle ones, which means that adding the extra context does sort of decrease the accuracy in the results. And then of the hybrid results, of the retrieval mechanisms, hybrid did outperform dense and sparse, and overall GPT-4o was the best model across the 10. And some probably talk about the statistical tests that were done. And sort of as evidence for the retrieval mechanisms, sort of this leftmost column here shows how, in terms of selecting the correct document, hybrid worked correctly 83% of the time. So that sort of reflects why the hybrid scores were much higher than dense and sparse. I'll skip over this, but essentially GPT 3.5 did perform much worse on the subset of the questions, and so that sort of indicates the increase in performance over the last year and a half, because it seems to have lower baseline knowledge about conservation, and also is less able to pass the information in the actions correctly. So now going on to the filtered set of questions, and so this is a set of 45 questions, still synthetically generated, but checked by conservation evidence experts. And so here we're sure that the questions are both clear and have one unambiguous answer. And so it's a slightly different playing field. So we had Llama 70B, Gemma 27B, and GPT-4o outperform the average human accuracy. So this was 6 conservation evidence experts who were very well versed with navigating the sea database. But I think it was sort of, from a statistical point of view, it was comparable to humans. What was different though is, so hybrid did slightly outperform humans when it came to retrieval, because we asked the conservation evidence experts who were taking the quiz to also let us know what actions they used to come to their answer. But I think the main difference is humans took, I think, on average like 2 minutes or so, whereas a model can do that pretty much in a second or so. And so we definitely do see a speed up there, although sort of in general, we're still dealing with multiple choice questions that don't necessarily synthesize across multiple actions, and of course don't necessarily reflect the nuance that comes into answering the conservation evidence expert question. And so I think that was clear as a project that I did at the start of the summer, which was to just hook up an LLM to the database. So it could generally pick up the right documents, but I think there's a little bit more work to be done in terms of fine-tuning and evaluating before we can have it actually set up as a chatbot website. But yeah, this is the I've sort of skipped past a few things, but this is the paper at the end of it if anyone wants to do any further reading. But I will open the floor up.
If you're really just a short one, and then my main question. So, can you give us like
Just one thing, actually, should we do questions at the end? Just be writing down, just so that we make sure we have enough time to hear it. Yeah, perfect. That's what do you try? So go for it. Do save up your questions, so please just do write them down. Just go through it. Okay, yeah. See that.
All right, cool. Okay. So, you're writing your conservation report, you're writing a paper, whatever, you're gonna need citations, data, sources, and so on. And there's quite a few different types of data you're gonna cite. You can cite academic papers, so academic publishing, you can cite a journal, a newspaper, that's all commercial literature. But a lot of your useful data is going to be great literature. And that comes in the form of those come in the form of NGO reports, for example, a UN report about how much countries are investing in conservation. You have the governmental publications. So again, an ICL report. These are all valid data sources, but they don't particularly exist in the common methods for publishing. So you don't find an academic database and so on. So a lot more difficult to find. Well, and there's actually a few problems with this. So, well, there's three main problems with literature. It's hard to discover. A lot of literature lives on the internet. And so, as you're familiar with, you have to be navigating through some nightmarish websites, drop downs. You're going to Google for a certain piece of literature. You're going to find in Google page 6, and no sane person really goes past page 2 when you're Googling. You're going to have a lack of standardization. You're looking for a certain paper, and that can come in a PDF, a doc, some LaTeX files. There's a lot of file types, and so it's a lot of things you have to learn to process through. And there's a horribly large number of files to look through. So when I reports from just the UK government, that's about 11,000 reports, and then you Google it, some simple file will be 26 billion results on Google. So this is very time consuming, really increase the man-hours required and the cost required to come up with these sources for conservation evidence. So we created a system to automate this whole. We create a pipeline to automate all this. And so how do we do that? Well, we need to collect some data, and we need to filter it down into some appropriate candidates that can be sent for human review. So CE maintain a database of the literature that they cited, and any organization that works with this morning data they have to cite will also maintain some sort of database. So we want a pipeline that can easily integrate with such a database. So as I collect data, filter it, we give it them for review, humans review, and we can store this in some database. So where do we start? Start collecting data. So what is the best or biggest stored data in the world? The internet. That's a lot of data. So how do we go about accessing the internet and searching for data? So you have a few ways. If you know your websites, you can access their APIs potentially. If you can't access the website's API, you can go and crawl it or scrape it manually. But that's comes with its own issues. We have the Internet Archive, which archives sections of the internet, but it only archives things on demand. And if anyone's accessed the Internet Archive, it's very slow. So it's quite uncomfortable to pull for a large volume of data. But then you have dedicated crawling services. And here comes in Common Crawl. So this is of their website. They basically maintain a free and open repository of workable data from the last 17 years. They have about 250 billion unique pages, and they add about 3 to 5 billion new unique pages each month. And they're a reliable data source. They've been used to train ChatGPT-3. So, as I say, quite reliable, and they are a good use case for us. So something that's relevant to us is, well, they have about 30 petabytes of uncompressed data total, of course, their entire archive. They have billions of unique files, and their second most common file type is PDF, which is what we focus on here. So a lot of academic publishing, or a lot of reports that are useful will exist as PDFs. So them being a high percentage of the database is very useful to us. But as I say, there's still 30 petabytes of data, and there's still billions of PDFs. That is still too much just to dump for human review. It's not realistic. So Common Crawl has a specific archival format on how they store their crawls, and we can kind of look how we do it, and we can process all of this and figure out what to do with it. So they store 5 different types of files. First, they store an index per crawl, which is a list of every billion, no, every few million web pages they crawl, they will store an index, an entry in the index, and it will be the URLs and metadata about that website. Then they store CDX files, which is not just every million or so, but exactly every website that they can crawl, again, associated with data. Work files, which are short archive files per website. Web files, which are the work files, but already processed for us. So it's a HTML, they will extract text for you. So this is good for processing websites, but not PDFs. And they store WATs, which are just the metadata from the works. So we don't use WATs. WEDs we can use for later in our pipeline to do website processing, but our main focuses are indexes to quickly search for relevant CDXs. CDXs, so we see what web pages were crawled by Crawl, and works, which is where we actually store the data we want. So a minor caveat with the data they store archive is that they only store the first megabyte of data, and that will come into our pipeline in a minute. So we first do an initial filtering. Pull up my notes. Where we on this? So yeah, first we do initial filtering from the indexes and CDXs, because we don't have to go and download all 30 petabytes of actual archival data. So each website has some metadata associated with it, some URL, file types, response codes, digests on the actual data itself, languages. We can use that in our initial filter pipeline. We can use the TLDs of the URLs. So we were given access to the CE database and some literature that they cite, and we narrowed it down to these TLDs being the ones that they currently use to cite files from, and decided to only focus on PDFs just for now in the pipeline, just so we can get a working proof concept. And the whole idea of this is we can change these filters on the go. This is a modifiable pipeline. So as we get later parts of the stages, as later parts of the stage improve, later stages improve, we can change our filters. So this is the run on 2 recent crawls through our first stage of filtering. So these TLDs we filter by response code and TLDs and file type. And these are results on 2 recent crawls. So we get about 2 billion in one of them a URL and 1.6 billion another one. Relevant about 11.5 million, nearly 9 million. So PDFs truncated, that is how many, as I said, only the first megabyte gets stored. So if a PDF is 1 megabyte, it's corrupted and it's useless to us. So we're going to have to call that ourselves into that, or scrape it. And so that's the percentage of PDFs that are truncated. Here are some results of this initial filtering. When I was looking through the data, there was a lot of CVs, an ungodly number of CVs, and shipping manifests, especially ones in Russian for some reason. But as luck has it, whenever you're writing a PowerPoint, I couldn't find any examples. But yeah, a lot of instruction manuals, but you do have a lot of goodies as well. So you have financial reports, we have stakeholder meeting reports, you have research articles, and then we have some advertisement for 3D genes. And so this is now the downloaded data, and this is some more information about the download. So this is the 2024-33. This is the actual downloaded data. So we got about 6.5 million PDFs from Common Crawl. We got all the ones we identified. Then the PDFs that were truncated and scraped ourselves, there's about a 92% success rate on that. The 7% as to whether these files don't exist anymore or it's just Cloudflare stopping us, I don't know, but combination of both. And then, but yes, 93% is still a decent success rate for scraping PDFs. And that comes about to an uncompressed size of 30 terabytes of PDFs. And that took 2.5 days for all the common core, so 6.5 million, and took 6 days roughly for the 2 million. And so this is just a folder in one of our servers where it stores all the PDFs for this scroll. And each one of these numbers is a folder, and that stores 10,000 PDFs. So it's still a lot of PDFs to filter. So we've collected millions of these random files, but it's still not realistic to submit for a human review. So we still need some sort of filtering, another local filtering stage. So what do? The current, what is hit these days is to shove a machine learning pipeline everywhere, and so we do as well. But as life has it, not everything is this easy. And so we come into a problem, specifically PDFs, and expanding the pipeline. PDFs are a bit of a nightmare. They are not a machine readable format remotely. They're basically a graphics rendering format. And so they don't encode text necessarily. They can be, if you have special characters or specific fonts, they don't even store the actual text itself. They just store stroke commands. So they'll just draw out text, and that's, you can't extract that out of a PDF realistically. Certain text can be encoded, and then you need an ASCII table to convert, or Unicode table, or an ASCII table, depends, to translate the encoded data into actual text like it's rendered. And the spec does not mandate ASCII tables and Unicode tables doesn't mandate that. And so you can see text if you open the document, but you can't extract. And then PDF 2.0 is almost 2,000 pages in the spec. It's basically nightmarish. And then what about different file types? As I mentioned, we want to also do doc and docx's quite soon, and most of the pipeline supports it. But then developing an ML pipeline per format is just completely unrealistic. So we need kind of some sort of standardized format for all this. And so what we decided to do is when you're reading a document as a researcher, how do you decide whether it's relevant? You decide by reading the text. And so we decided to do text extraction in every file. And we store these as JSON files. And for each PDF or just any file in your pipeline, we extract the text, store it, and then any other metadata you want with it, and we dump in the JSON. We use new PDFs specifically in our case to extract text or PDFs, and then we store these JSON files locally, and then we can then send them to Shrey's machine learning pipeline. So this is kind of bringing everything together. So we source our data from Common Crawl and the internet. We can, if it's not stored completely on the Common Crawl, save it locally. We do some text extraction, standardization, saving all to JSONs again locally, and then we can pipe those files through a machine learning pipeline which Shrey has developed, and then finally submit those in a realistic number into a database for human review, which then can be integrated into a final literature database. So the state of my project, and some lessons learned, is following scraping guidelines. Not every website wants all the data scraped. We've learned that, and so we kind of scrape the holes in the internet scraping, and there's also performance issues. As you saw, it took about 6.5 days just to do the scraping for one crawl, but it took 2 days to get the common core data. So we're doing, and the actual data size is much smaller for the crawl size. So it's about 9 times slower. So there's also performance concerns there. So scraping has been put on hold, but common core data we still use that. We need to finalize docx support because there's still a lot of useful files on docx's. And then data processing, just some notes. Shepherd is the server we've been using for this. Processing PDFs is quite fast using PDF. We're still limited by disk speed, so just we need more hardware. New PDF had some problems with developing it. This took up a lot of my time. I had to go into the source code and edit it. There's a bug submission, so this is actually quite useful for the new PDF project as well. There's still some PDFs that cause new PDF to segment, so more bug reports need to be made. And then this is minor caveat. Certain PDFs are just scans, and most useful PDFs are not going to be scans. So this is not too big of a concern, but for in the future, if you want to process truly everything you have, we will need to do OCR. This is slow, so this is again just a performance concern. And in the far future, it's adding, we'll get this true production, adding support for more file types, and adding some GUI so it's maybe more usable by the researchers. And yeah, that's a fully full pipeline for automating this. And Shrey will now go into detail on the machine learning.
Yeah, so yeah, now we're on like the machine learning part of it. We've got all of this data from Kacper. Now let's try and find the good bits essentially. So let's get a general look at the top pipeline. NLP quite naturally lends itself to this two-stage process. So we start by pre-processing it, like cleaning, formatting it, etc. And then we start the classification part. Particularly for this project, we have both the mostly irrelevant data that Kacper sent us, the colorful diamonds in the rough, and we have some sort of relevant data, which are like ground truth. And we'll have to scrape the relevant data for us. Additionally, on the classification side of things, we'll split into 2 layers of models with different kind of targets for what we want them to do. And this lets us be like as efficient as possible rather than having one jack of all trades model. This is kind of the training pipeline, what it's going to look like. So we start by feeding in the irrelevant data Kacper's given us, and we clean it all up. And at the same time, we scrape up the relevant data, and then we can merge it all together into one massive data set, which we then feed into our models. Note, both models are going to train off the entire data set. We're not restricting anything here, and that will give us our parameters, which we then use for inference. Inference is a little different because we don't really care about relevant data. We're just looking at all of those millions of PDFs that Kacper's found. We feed them straight in, clean them up again, and then we send them through model 1 first. So model 1 is a kind of very fast, less intelligent model to try and just remove the vast majority of irrelevant files that are out there on the internet. And then that creates kind of potential conservation articles, which we then feed into model 2, a more intelligent but more complex model, which then does a kind of a much better form of processing, and that will output our relevant data, or at least the few gems we think we can find. Conceptually, I like to think of this as a pipeline with several layers. We have level 0, which is all of the pre-processing steps. Level 1 is our first model, level 2 is the second. And between each level, we have kind of data banks, which is where we'll be saving kind of the results. These are like half layers sort of, and level 2.5 is our final output. This kind of lets us have accessibility and change it as we want. We can take out model 1 if it's not being particularly helpful, or if further on we think we want extra models, we can add in like layer 3 and a level 3.5 as our final output. So it's very easy to kind of add on to this general approach. Let's get into some details. So level 0 first. We start with Kacper's irrelevant data, which we just load all of those batches in the JSONs he's given me into QDF. QDF is very similar to Pandas, which I'm sure some of you have used, but it's accelerated by the GPU, which is going to be very important because we have a computer with a very powerful GPU. So we'll just validate all of those PDFs. There's some corrupt documents in there. That's fine. We can just refetch them. It only needs to be done once. That gets saved into level 0.5. And then we start scraping relevant data. So using the database which Radhika was talking about, all of the conservation evidence's work, we can use that. There's studies, which are the relevant material. There's synopses, which are kind of the long-form PDFs. And then there's actions, which are, information about the actions and their effects. We scrape all of these together, pull them off the website, write them to level 0.5 as well. Then we just need to merge them together. So we make one massive data frame, label everything either relevant, irrelevant, and so on. And then we do the usual kind of NLP stuff. So that's like removing stop words. That's words like the, a, and, etc. And then we tokenize it. So split it into like each word, take the stems, all of the usual stuff. And now we've prepared our data set, ready to train. This takes us into the first one. So right now we have a massive data set of PDFs. And a ton of them are really long, like 100 pages. So level 1's models were our objectives. We need precision to be really high. Like, even if we have a fraction percentage of false positives, with millions and millions of relevant data out there, that's going to completely overshadow like our true positives. So we want precision to be absolutely important. Recall is also quite important. If you've only got like 5 good articles in like 100,000 things, we don't want to miss out on that. But overall, the most important thing, it's got to be fast. Like, this is going to take ages to run if it's not blazingly fast. And so for that reason, we use a simple option. Logistic regression, nothing too fancy, just a simple function. And for maximal GPU usage, to accelerate it as fast as possible, we're using NVIDIA's Rapids suite of tools. So QDF, which I talked about earlier, the Pandas alternative, is one of them. We also have QPy and QML, which are kind of, you can think of them as analogs of NumPy and scikit-learn. So first off, we have text right now. We need that to be a vector. We want to work mathematically. There's a bunch of different vectorizers we can use. So count vectorizer is just, count the words and put them all into a vector. So the value of every kind of element is the frequency of its corresponding word. TF-IDF is very similar, it's that function over there. Don't worry about it. Both of them are slow. They're not useful. Instead, we're using a kind of hashing vectorizer. So this kind of takes the word, hashes it to produce an address, and then stores its count in that address. There's a small chance of collisions, but oh well, like, it's fine. This is way, way faster, especially when it's GPU accelerated. We have vectors of constant sizes, we can be much more consistent. It's great. So from now on, we've got our vectors, and this part's simple. We just use QML's logistic regression classifier. This is very fast. It's 300 documents processed per second on our, I think, RTX like 3090. And it's also extremely precise. Like, those are very good numbers to me. And most used for level logistic regression outputs a score, so it's a number between like 0 and 1. And then it classifies it on a threshold. We can change that threshold. You know, if we just rank all of our documents and we say, I want the top 100, top 200, top 1,000, we can control how many documents we get, which means for level 2, you know, we control the input side. So if it's too slow, we just give it less documents. It's fine. Speaking of level 2, let's get on to that. So now this has very different requirements for the model, because we don't have to deal with tons of documents. We choose how many documents we have. So now at this point, the recall becomes way more important. We've only got like, you know, these 5 relevant documents in the 10,000 are now 5 in 100. We really don't want to lose them after all this work. So we want it slower, we want more complex and accurate models. And yeah, like I say, embeddings are a good fit. Embeddings are another way of turning text into vectors, but you can think of them as more encoding the meaning of a text. The famous example is if you take the vector for king and you add the vector for woman, you get the vector for queen, which is quite impressive for literally just numbers. So there's thousands of embedding models like publicly available on a website called Hugging Face. It was, you know, just run through all of them, find the best rate of speed and accuracy. I think I ended up using Absolutario's like gist embeddings, but that's not really important. What is important is that they have a limited input size. So embedding models, whereas before, logistic regression, we could just we had our fixed size for the hashing vector. This week takes about 512 tokens at a time. And that's it, it'll just turn that into a vector. But our documents, remember, are like 100 pages. Like, they're massive. So we have to chunk it. And this is a little example of chunking. So if you take every 5 characters and then overlap them, so the first 2 of the next step are the last 2 of the previous one, that means we don't lose any context over that like boundary of the chunk. So kind of making 512 token size chunks across the entire text, it gives us a way to turn a massive PDF into a series of classifications, which we can then bring back together later on. We aggregate them at the end. And just a majority function is an easy way to do that. You know, if most of the document is conservation relevant, the whole thing probably is. So now we need to classify these embeddings using some sort of vector analysis thing. Very conveniently, literally a couple of weeks before I got started, IBM released FastFit, which is a very, very efficient embeddings classifier. So it's few-shot learning, which means essentially rather than needing to run it over like, you know, a million training examples to get something good, you can give it even just 5 and it'll get a pretty good idea. You give it 10, it'll get an even better idea. So this made it way faster to train. We didn't have to let it run for like hours and hours and hours. But yeah, the library was also brand new. So there was a similar pains of having to go fix, modify the whole thing and, you know, add functionality. But the good thing about that is that I could customize it to our use case, which is always useful. And then, yeah, lots of hyperparameter tuning, choosing context sizes, choosing models, choosing embeddings classifiers. Lots of optimization. These are the results we end up getting. This is way slower than we had before with QML and with logistic regression. It's only 40 documents per second, but cool and accuracy are really good. And they have a more kind of intelligent perspective on the documents. It won't just kind of blindly classify a lot of things into being the same. So the inference pipeline, now that we've trained both of our models, inference is really simple. We just take a massive batch of relevant documents, we run it through, we pre-process them, we run it through level 1's logistic regression classifier, and then that gives us level 1.5, which are documents we think have potential to be relevant. We then run that through level 2's fast embedding classifier to get level 2.5. And then we rank them. These are some of the top documents that we extract by the classifiers. You can see, you know, they're generally actually pretty relevant. Like, you know, with any luck, these will be helpful. But it's still not perfect. I don't know, this was the 4th best one out of like 20,000. I don't know what this is. But yeah, on the whole, it's pretty useful. It runs like very fast and actually produces pretty good results. So yeah, any questions?
Thank you, Richard. Now ask questions of anyone. I think we have about 10 minutes. So.
Yeah, I mean, first of all, congrats guys, this is really impressive. And an internship, this is super cool. So yeah, my question is for Radhika, I assume. I was curious, like, can you give us an idea of the questions that are generated by Sonnet? Are the answers to these questions very clearly just lifted from the source materials, or did they require any sort of like, maybe like one step more reasoning than that? Or like, is it just easy comprehension from the text?
It was mainly sort of easy comprehension. I think the one thing to note is often for coming up with the so-called incorrect answer, but we want to definitely be taken out from the text. The incorrect ones sometimes were just sort of like negative correct one. And so that's why we really needed to have the sort of automated filtering stage, which basically uses checkout similarities, so it calibrates the similarity between sort of making both each of the answers answer the question that included variant. So we had to manually set thresholds so that the answers were varied enough. In terms of their correctness, I think we did definitely have quite a few good conversations about you know, whether sure the one correct answer could definitely be a correct answer, and so generally did quite well with that. But is it possible that one of the other three incorrect ones have been intelligently sort of by them as potentially being also correct? And so I think because in the end we were just testing one action per question, that didn't really affect it as much, because if you retrieve the right document, then hopefully it's able to reason that that answer is correct, but it's definitely not.
I mean, the reason I was asking was I'm curious if you have any like answer or even a guess or an intuition to why Sonnet did so relatively bad on questions that it itself wrote.
Yeah, it was quite interesting because especially at the start of the summer, Sonnet was by far the best LLM for generating the questions. I mean, maybe it's very good at, we had a very like long specific prompt for how the questions were generated. It was about like 20 or 25 sentences. And so maybe because it had so much instruction, it was able to generate the types of questions that we wanted. But in terms of actually passing the information and answering them, it was specified. And so in a way that sort of indicates it actually did quite well with sticking to just the documents and the action to generate the questions. So in that sense, maybe that could be it, but beyond that,
Yeah, thank you.
Thank you for the talk, very impressive. I have a question about the language. So is the LLM able to deal with all of the languages available in the website, or is mainly targeted at English and other major languages?
For us, it was just in English because we were just looking at all of the actions on the conservation database. So I mean, right now that's in English, but I think there's probably potential. There's probably a want to move to different languages as well.
Because I find like sometimes there's a discrepancy on like the data availability and the geographic regions of importance for conservation. Let's say in Indonesia and Brazil, many conservation patterns there, but the language is not in English. Very impressive.
Kacper, how many languages did you encounter in your exam?
Well, scraping the language, because it's knowledge now. But we did in the initial filtering also just done a very quick filter. Well, once you download the data, while we were processing the JSONs, because we're just focusing on English again, just for proof of concept, which is a really basic filter. It was just checking does it contain the top 10 most common English words. Does it have this percent ASCII characters? Yes. We continue processing it to the JSON, and then Shrey's Python again probably pick up English documents because we trained it with English documents. So yeah,
in general, like embeddings models tend to be like fine-tuned on English, so like they wouldn't make it through most of the models. I don't know why the random Spanish one.
Yeah, but scraping was they scrape everything. They have the report is excellent because you can get any and every language. We had, yeah, as I say, when I looked for the data, every language is there basically. A lot of Russian shipping manifest, as I mentioned. Yeah.
So one thing I noticed is that a lot of the Spanish ones have an English alternative in embedding there as well as in the PDF.
Yeah,
So I wonder if those are English as well.
I think like my theory is that like there are like there's a kind of like watermark over it, which I think is what we picked up on. But again, the watermark isn't conservation relevant, so I'm not entirely sure. Any more questions?
You mentioned that you're running the Cloudflare briefly. So these kind of crawls now, the internet is very, very hard to crawl now because of Cloudflare. So how much did you run into captchas and sort of automated things that would just stop you?
So, as I say, from 7% of fail, I couldn't tell you what is the documents not existing and what is actually how for stopping us. Basically, when it's crawling, it makes sure that the response it gets is from the URL. It's not a redirect. It has to be a response from the URL we're trying to scrape, and that is the same MIME file type that we're requesting. And then we also do some small verifications. So it's PDF, you just check is it about a PDF. So you got a start of PDF file marker and you got end of file markers of PDF, so you check that. And if it matches all three, it's probably the file we're looking for in the archive. So we save it. But yeah, if it's a redirect, it's a HTML, which you know a capture from Kacper, we just ignore it. We just classify as a fail. We save our fails, so we could potentially again develop is amount of things to do. Another pipeline which could take the fails and then reattempt to get past them because there's Python libraries that try to get around Cloud or automate captures and so. But yeah, we store fails so we can in the future we try to go.
So I want to just question clarification. So maybe Alex is part of you as well. There's sort of three levels of conservation element one can think of. You know, something that the experts know about, which you guys have been doing for some years now. Then the big crawl of the legitimate data in the journals and so on, and then this grade, right? In terms of the value, how would you rate the three? Or how would you guys rate the three when you guys been seeing all of them?
I didn't care about Russian shipping manifest.
Wow. Yeah, it's also controversial, but I would say, well, I think first thing to say is that most conservation literature is in English and academic journals. There is, though, a huge proportion, I think it's 33% of the conservation literature is in non-English languages. So, and I think the big thing that brings, while that's valuable, is that, like someone was saying, I think that you get data from places that are very underrepresented in the English. So you're filling a lot of gaps in if you're looking at where the evidence is from, you're filling in a lot of gaps in different parts of the world that you haven't represented. The grey literature is an interesting one. I think from our experience, you don't because conservation evidence does include some grey literature. Not a lot, but it does include some. And our experience is that the success rate of finding relevant stuff there is a lot lower than for anything that's in English or non-English in academic journals. So yeah, so it's more of a needle in a haystack, probably that one. So in terms of priorities, I think yeah, academic literature is one, but not to say grey isn't useful. It's just probably I would say it's slightly less useful. Yeah.
Okay, I just note that there is a group trying to come in here any second now. So let's thank the speakers and
But